We turn now to a very important model that played a seminal role in the history of connectionism, and that's the perceptron. It looks nothing like the illustration, unfortunately, that has a great name. This was an early model developed in the 1960s, and a supervised training method did exist for this. So given a desired mapping from input patterns to output patterns, there was an algorithm for finding the appropriate weights to implement that mapping if it existed. This is what the perceptron actually looks like, not nearly as flashy. It's a two-layer network. So we only have input units and output units, no hidden units. At the input layer, we're going to provide the patterns. And the output units have, originally they had a stepwise activation function. That's why there's a step shown in the middle of each of the units there. What they do is they sum their input in the usual way. And if the input is less than some threshold, the output is 0. And if the input is greater than some threshold, they output a 1. Very, very simple. Now, the term perceptron is sometimes used loosely in the literature to refer to a broader class of networks. But strictly speaking, it's a two-layer network with a discontinuous stepwise activation function at the output units. The algorithm to train it was the Perceptron Convergence procedure. We won't be doing it in detail because it's consigned to the dustbin of history, but it works much like the algorithm we will be using, backpropagation. So we start off with input and output pairs. And to give you a flavor of the algorithm, it's as backpropagation 2, it's a credit and blame algorithm. So consider the perceptron shown there on the bottom right. If we observe an error for a specific pattern at the third output unit there, then we ask how much did the first input unit and its associated weight contribute to that error, and we ask the same question for all weights in the network. So there's a specific question to be asked of a specific pattern that addresses the contribution of this unit and this weight. The Perceptron Convergence procedure requires an explicit teacher. It's not like Hebbian learning at all, in that we have to tell it what the right answer is. It has a limitation, though, that's a bit like Hebbian learning, which is that similar inputs will produce similar outputs, which is not necessarily a bad idea in principle, but it restricts this network to learning something similar to correlations again. Furthermore, there was an analysis done of the theoretical set of problems that the Perceptron Convergence procedure can solve. And it demonstrated clearly that there was a whole class of problems that it couldn't solve. So we're going to have a look at one of those. XOR is called, X is the abbreviation for exclusive OR, which is a logical function, which we're going to look at now. So we've met one logical function before. We met AND. These are not real-world machine learning problems we're going to survey here. These are logical problems that serve to illustrate the character of a class of problem. So here we have a perceptron with two input units, and I've shown the bias unit there as well. And in the truth table, you can see the desired output for each of the 4 input patterns. That exhausts the domain. We're only interested in those 4 input patterns. And basically the output is 0 unless both inputs are on. And you can see, furthermore, that the weights that are given here solve this problem. If only one of the 2 output units is on, the other has 0, and the bias is sufficiently big to ensure that the output unit never exceeds the threshold of 0 here. But if they're both on, then we get 1 times 1 plus 1 times 1, which is a net input of 2, and the bias unit is no longer sufficient to keep that below threshold, and so the 4th pattern with 2 1s produces a different output. Now I've shown the 4 input patterns in the lower plot. This is a plot in input space. So each possible input pattern consists of two numbers and therefore can be represented as a dot in input space. And we can understand what this network is doing by seeing it as partitioning the input space such that if the summed input, including the bias, exceeds the threshold, we're on one side of a line, one side of a category boundary, and if it doesn't, we're on the other side of that boundary. So any combination of inputs that lies above that dashed line will produce a 1 at the output. Any combination of inputs that lies below that dashed line will produce a 0. Very simple and easy to solve. Here's a similar problem using the same input patterns but with different output patterns. This is logical OR. So logical AND and logical OR play a very, very big role in any formal logical system, including the basis of arithmetic. They're rather uninspiring functions, though, it must be said. Here, the problem is slightly different in that if either of the input units is 1, then the output unit will pass its threshold and will produce a 1. That applies if one or both of the input units is 1. The 4 patterns are plotted as before. They're the same 4 patterns, so they lie at the same 4 points. But the dashed line that serves to partition the input space has moved now. We can call this, if we want to be fancy, we can call that dashed line a discriminant function. Ooh. Okay, so AND and OR are both very, very simple. Here's exclusive OR, and this one causes problems. You can see the 4 input patterns are the same again. The output is desired to be 0 if the 2 inputs are 0, or if the 2 inputs are 1, and to be 1 if only one of the inputs is 1. This cannot be learned by a perceptron. A perceptron cannot solve this problem. And we can kind of get an intuition for why this is if we look at the patterns in input space again. The 2 red dots are the 2 patterns for which a 1 is the desired output, and the 2 blue dots are the patterns for which a 0 is the desired output. Now there's no way to fit a simple straight line that can partition this input space such that the red dots lie on one side and the blue dots lie on the other side. We say formally that this classification is not linearly separable. So there's no straight line you can draw, or no linear discriminant function you can draw, which will separate the 2 classes that we want the network to discriminate among. So a perceptron cannot learn problems of this generic class. And furthermore, in the 1960s and 70s, it was known that if we were more generous with our architecture and we used hidden units, then we could find weights that would solve this problem. So up on top, I've shown the input space with the patterns as before. The network now has 2 hidden units. They are likewise stepwise activation function units. The bias units, biases are shown as little numerical values to the left of the units here. And there's a set of weights, and you can verify for yourself that this set of weights accurately solves the problem. What this means formally, again, an intuitive way of thinking about this, is that adding the hidden layer allows us to re-represent the 4 input values in a different space, in hidden unit space. I've shown this with no particular concern for numerical accuracy. On the right-hand side, the lower plot shows hidden unit space. These are the 4 values that the 4 input patterns produce at the hidden layer. And here now you can see that it is possible to draw a straight line discrimination function that keeps the red patterns on one side and the blue patterns on the other. I said I drew this with no care for numerical precision. You might like to draw this yourself using the actual values that this network would produce to verify that this is true. Now, in all these 3 cases so far, the perceptron has been used as a classifier. or rather each output node, of which we only had one, is a separate classifier. Its output is 1 or 0, and the experimenter will interpret that value as meaning that an input pattern belongs or does not belong to a specific class. If the two classes are arranged in such a way in input space that we can drive a straight line between them to keep one class on one side and the other class on the other side, then they are linearly separable. And the Perceptron Convergence procedure is guaranteed to find a solution that correctly classifies all the items in the training set. And if they are not linearly separable, it won't. We can add hidden layers, but at the time the perceptron was developed, there was no training procedure for training the additional weights that we've put into the network now. That was the problem. Here's an example of a bunch of patterns in a variety of input spaces. At the top left, we see two classes which are easily linearly separated. Bottom left, we see the same. Up at the top right, we see a classification problem where we need to draw a wavy line in order to separate the classes, so they're not linearly separable. They're almost linearly separable, though we might be able to do better than nothing there. But the two lower right plots, the nonlinear plot and the inseparable plot, demonstrate two cases where it's hopeless. Either the two classes are just completely confused, as in the inseparable case, or the nature of the boundary between them is nothing like a straight line, as in the nonlinear case. Now, history comes along now, because in 1969, one of the founders of MIT Media Lab, Marvin Minsky, who died a few years ago, together with Seymour Papert, also of MIT Media Lab, they wrote a book analyzing what was known about such networks, about perceptrons. The book was called Perceptrons. It understood perceptrons to be two-layer networks, and they had available to them no training procedure for networks with more layers than that. And they proved that the Perceptron Convergence procedure couldn't train the more complex networks. They were right in a sense, but their contribution was most unfortunate. Their pronouncement that the more interesting problems could not be solved by perceptrons killed the field of artificial neural network research for a decade. Most people left the field. There were a few stalwarts exploring other avenues, but interest had begun to turn towards automated learning. People were getting data consciousness. They wanted to do supervised learning, and this seemed like a dead end. It's a great shame that they killed it in this way, because the tweak needed to go from the perceptron convergence procedure to backpropagation, which famously can solve all these problems, is tiny. It involves no more than the introduction of a very, very simple bit of high school calculus. There was no awareness of this by Minsky and Papert. And it's very regrettable that this happened, but this essentially is why we distinguish between the early networks where there was no training procedures and the renaissance of connectionist work then in the 1980s. So 1969, Perceptrons, that book kills the field, almost stone dead. And it's not until the appearance of some more books, the parallel distributed processing books in 1986, that the field suddenly bursts into life again.